I'm Matti, as you heard, and I'm here today presenting the work of two of PhD students who actually made most of the work. So I really want to highlight them in a first place, that this work is carried out as a part of Charisma Marie Curie doctoral training network, which was done in and this is a specific network done in a collaboration with industry. So these students have been spending half of their time in industry and at the same time doing the PhD work. So it's in that way, it's quite challenging for them, and also it has been also that they have learned quite a lot how you can make these products or devices or utilize these technologies in actual products. So I really want to highlight that this is the collaboration with the Nova, Ynvisible, and Tampere University, and you can find more information about the project on its webpage. So giving you a little bit understanding what we are doing over here, a small context shortly, that the smart labels, you know them very well. There is many different applications in packaging industry, or where you want to monitor certain information and give the indicator in terms of display as an example. Plenty of different, let's say, application domains. So in this particular research, the focus was really on irreversible visual indicators. So IVIs, I'm going to use that one. It's much easier to pronounce for the Finn. So over here, we use the IVA to make these smart labels. And especially for certain kind of application, there is a need that we are like fixed threshold. A certain kind of condition, let's say temperature, impact, or something else, like time. And once that is reached, the display is changing the color, or some kind of indicator for the consumer, as an example. And what does the irreversible means over here? That basically the label is a tamper proof, meaning that once it has been changed, for example, here electrical potential has done, there is a color change, and then it does not come back. So this is the important part for these IVIs in particular case. So in our approach over here, we develop the IVIs via In-Situ Electropolymerization, and these indicators are produced by the solution monomers in the electrolyte of a vertical device. You see the vertical device over here. We have the electrodes, then we have the electrolyte and the monomer over here, and then there's the adhesive over it. And basically, once the monomer that changes the color over there, then there is a reflection immediately. So from transparent to a colorized. So the key parameters for such a device is let's say from electrical and optical point of view, a couple of things, and we can adjust and fine tune these indicators by carefully selecting right polymers to be used. And as an example, using a monomer with a lower oxidation potential, that will lead to a lower activation potential in the device. And if you're starting with the dimer or trimers instead of this monomer, that will lead to a lower starch consumption and a higher colorification efficiency. So in this study, we use these 4 different monomers available commercially, E.biethanol and tetbiethanol. And over here, you can see the CV curves. So basically, it means that once we started to rise the voltage, after the activation, the current starts to flow and change the colors. So based on that one, we can define the activation potential. Then at the same time, it can be measured how much the color or how much current is needed. So basically charges to have the colorization effect. So for example, here you can see the charges needed to the optical density of these devices. So basically, both of these parameters are important when we are designing a low power device sensors. So these sensors, indicators will be then transferred, changing the potential over there. So we need the energy storage unit in the label. There are a couple of alternatives. One would be to have the battery, and the other one would be basically having a supercapacitors, what has been investigated over here. So if you don't know what is a supercapacitor, it's basically a device that stores the energy electrostatically, which means that they are storing the energy over here in this double layer form. So we have the one capacitor in the other electrode, we have the other capacitor on over here. So that's the reason for the double layer. And then we have the electrolyte over there where the ions can move. So when we are placing a voltage over there, it is charging, the ions are transferring to the one end and stored on these electrodes. And it's therefore really important that we have a high surface area. So basically, with the higher surface energy, surface area for the electrode, the more material or more charges we can store into a single device. So a couple of things about the supercapacitors. If you are thinking about them, they have typically have a high energy, high power density, but not so good power density, not so good energy density. So if we compare them, batteries typically high energy densities, and the supercapacitors are good if you a high power density, if you need to recycle or recharge. So they typically have a much higher cycle lifetime, just because they are these electric double layers. That gives you that opportunity, and also extremely fast charging. So if you let's say think about it in a way, this is just a really simplification, that if you have a barrel of water and you have a small hole in it, so from the battery you get a lot more energy, but you get it only small. And then a supercapacitor is more like a bucket, so it's much smaller, and you throw all the energy out of immediately. So the supercapacitors, we fabricated that one completely by printing. Starting from aluminum PET film, printing first the graphite as a current collector layer, then activated carbon on top of that one as an electrode, then having a paper substrate separator there, laminated another similar layer on top of it. And basically the electrolyte that we used, that was aqueous based with the salt, so natrium chloride. So these are really sustainable devices already. The challenge of the water-based supercapacitor is that we can't charge them so high. It's only 1.2 volts, which will be limiting into many different applications. So having said that, we can definitely then connect these supercapacitors more in a series. And the experimental setup over here has been that there has been first separated supercapacitors charged up to 1.2 volts over an hour. So they have been completely charged. Then 2 or 3 of those connected in the series to drive these IVIs. And at the same time measuring the voltage over there. So here you see some of the results. So all those 4 IVIs were tested. Here you see the first one. And I think what I want to show over here is that if you see, for example, what was the activation potential over here. Here you see the voltage of 3 volt, 3 cell supercapacitor. It decreases up to that 2.4 volts. But they also get quite nice a change of the transmittance, so meaning that we get the really good colorification. But for example, when we have the 2 cells in a series, it's really on the limit already in the early beginning, meaning that also the colorification of that one is not that much. So basically, this is one part that is partially limiting the usability of this material. Then here are the results of the others. Let's start with the bioethanol. over here. So we get the full activation with the 3 supercapacitors in a series, but the transmittance with the 2 supercapacitors hasn't really be able to do the work. So we really don't get the full change on the colorification over there. But then if you are looking more on these other materials that had also much lower the activation potential, as I pointed out in the early beginning, in those particular cases, we see with the 2 and 3 supercapacitors in a series, we are able to identify the changes. And as in both of these cases, I think you see the battery as, there's a 3-volt coin cell battery shown as well. So the impact with the 3 supercapacitors in a series, the changes happen, the colorification change happens much faster. As an example over here, here we have the 3-volt coin cell. It doesn't actually go even so good till the end. And for the supercapacitors, it is much faster. So basically, all these together, these experiments are showing that this can be done quite effectively with using the supercapacitors. So shortly in this paper, what has been shown, so you can, of course, look more detailed on the papers, and we are at the moment preparing a journal paper also, which will be more investigating how these devices can be combined together with the other switches, so that all these things, and we can have really energy autonomous labels that are charged in the early beginning, and then they are monitoring the temperature and doing the activation. And that work was out of this paper here today. So finally, I think I'm almost used my time. So finally, I want to thank for you all of the attention over here. I want to thank the project over there and the funders. So this is funded by the European Union. And if you have any questions, I can try to answer.